Hello everyone, today we are very glad to introduce our work, PerfEstimator, a generic and extensible performance estimator for data parallel DNN training. Today, distributing the training of deep neural networks, or DNNs, on clusters like cloud servers is the de facto solution for scaling modern DNN systems. In the distribution of DNN training, data parallelization is widely adopted due to its simplicity. However, many recent studies suggest that data parallel DNN training faces a significant scalability problem. It is more economical and promising to first predict the performance implications of DNN systems at large scale to give early feedback. Existing works on performance implications of DNN systems adopt analytical modeling, which is lightweight. However, they often fall short in capturing the increasing system features, like optimization for faster training. So, we propose a generic and extensible performance estimator called PerfEstimator, which is both lightweight and extensible to cover increasing new features. Now, we will introduce the design of PerfEstimator. First, we built PerfModel, an attribute-directed acyclic graph-based performance model, capturing the training workflow, which is extensible to incorporate new optimization features. Next, we built PerfSim, a single machine scale simulation framework consists of computation profiler and communication simulator. Finally, we built Estimator, which is driven by our computation and synchronization pipeline to estimate training performance and scalability. These three parts make up PerfEstimator. Users can set configurations containing network communication configuration, DNN structure, and hardware configuration. With this configuration, PerfSim will output the necessary data of time cost of training processed through profiling and simulation. PerfModel will use the data to complete the attributed DAG. Then, Estimator builds the computation synchronization pipeline and predicts the training performance and scalability of the system. This is the high-level architecture and workflow of PerfEstimator. Next, we will take an example of training a simple 3-layer CNN to introduce the detail of PerfModel. In the timeline below, blue stands for forward propagation, and green stands for backward propagation. This CNN has 3 layers. Conv, AC, FC stand for convolution, activation, fully connected layer, respectively. We can abstract each layer as a computation operator. In the forward propagation phase, these 3 operators are executed sequentially. The errors present happen before orderings. In the backward propagation phase, these operators are executed in sequence, but in a reversed order. Fully connected and convolution layer will produce gradients, which needed to be synchronized. Here, we use all-reduce operation to synchronize gradients. Before all-reduce starts, an operation called negotiation, or NG, is performed to assure that every trainer is ready for gradient synchronization. Now, we can add the synchronization operators into the attributed DAG. The same with the convolutional layer. The operators in training construct an attributed DAG in which the time attribute of each operator is reported by PerfSim. To demonstrate the extensibility of PerfModel, we take gradient compression as a performance optimization, for example. We add 2 new abstract operators C and DC, stands for compression and decompression, respectively. After the gradients are produced during backward propagation, they will be compressed for transmission and decompressed for reduction. In our abstraction, compression happens before negotiation and decompression happens after all reduce. Then we can construct a new attributed DAG to cover this new feature. This example shows that new features can be easily added into Perf model as long as we have the execution dependency of operations. As for profiling and simulation, in PerfSim, we take full advantage of existing tools. For computation-related operators, we use existing built-in profilers in mainstream DNN frameworks. For synchronization costs involving network, we use SimGrid, a simulation framework for MPI communication. Finally, we'd like to introduce the computation synchronization pipeline built in PerfEstimator. It will project all operators in the attributed DAG built by Perf model into a conceptual timeline with their time attributes. Here is the projection of forward computation operators, and the length of boxes is the time cost of operators. Now is the backward part. Because the fully connected layer is executed first in the backward propagation, and it will produce gradient to be synchronized. The negotiation and or reduce operator of this layer will be projected just behind the backward computation of this layer and can be paralleled with follow-up computation operators. The same with convolution layer. However, its or reduce operation cannot be paralleled if the trainer has only a single port network interface controller. Thus, or reduce of convolution layer will be started right behind or reduce of fully connected layer. Now, a computation synchronization pipeline for an iteration of training is built. To predict performance, we define scaling factor alpha as the ratio of computation time and total time in a single iteration. Alpha is always smaller than 1 in distributed training, and the closer to 1 means the better scalability the DNN system has. With the scaling factor, we could easily predict the scaling performance from single machine performance using following formula. After introducing the overall design, we'd like to introduce the part of our preliminary evaluations. First, we validate the accuracy of performance prediction at a relatively small scale with up to 12 nodes. With VGG13, we achieve less than 3% error. Here, we also compare our results with a related work, Paleo, which only adopts analytical modeling. When the cluster size increases, the prediction accuracy of Paleo keeps decreasing, while results of PerfEstimator remain roughly unchanged. Next, we use gradient compression as a use case to study the extensibility of PerfEstimator at large scale. As the light blue curve in the figure shows, the predicted training scaling performance when 10 gradient is used is better than the original training process, since it largely reduced the amount of gradients exchanged per iteration basis. However, our simple simulation also tells that the improving factor drops when the scale becomes extremely large, which further suggests that the standalone gradient compression is not sufficient and perhaps needs to be combined with other optimizations. Finally, comes to the conclusion. First, we propose PerfEstimator, a generic and extensible estimator for accurate performance estimation of large-scale data parallel DNN training. Second, PerfEstimator consists of Perf model, PerfSim, and Estimator, constructing a computation synchronization pipeline to give performance and scalability prediction. Third, with PerfEstimator, we can accurately predict the performance of data parallel DNN training jobs with a low prediction error. And that's all. Thank you.